Moltex Energy Canada recycles nuclear waste and uses it to produce more clean energy. They can store energy, supply to the grid as needed, and produce heat for hydrogen. Today, I welcome Rory O'Sullivan into the studio to talk about the process behind recycling nuclear waste. Hi, Rory. Thanks for joining me today.
Hi, Maria. Nice to be here.
Welcome to the Reimagined Energy Podcast.
Thank you.
So tell us about Moltex Energy and how your organization came to be.
Yeah, sure. I'd be delighted to. So Moltex Energy was founded by Ian Scott and John Durham in 2014. And really they had one goal in mind, was to develop a nuclear technology that could produce low cost, clean energy for the developing world to displace fossil fuels. In addition to dealing with the challenges of nuclear power, and the main Achilles heel of nuclear power is nuclear waste.
Mm-hmm.
So since then, over the past few years, we've been developing a technology that can take the existing waste that would normally be radioactive for very long periods of time and use it in our reactor as fuel, recycling that, reducing that energy. So things took off for us in 2018 when we were selected by New Brunswick Power to develop and demonstrate the first reactor there. And we've been building the team in New Brunswick, that's where I'm based, since then, and getting ready for the next stages.
Well, you have three unique technologies, that Moltex offers. What are the three, technologies that you have?
So there's the reactor itself. This is a small modular reactor. It's specifically designed to use recycled waste as its fuel source.
Right.
It's called a molten salt reactor. So the fuel is actually a molten salt, but it's small and simple and relatively inexpensive to build and operate compared to traditional large nuclear facilities. It's passively safe, so there's no human intervention needed for shutdown, or it's extremely safe. And in addition, it can produce high temperature heat for district heating, hydrogen, other industrial uses. So this is the new era of nuclear power, can produce energy more than just for electricity, to decarbonize those other harder to reach parts of industry. So that's the first one, the reactor.
Mm-hmm.
And because it's designed to use that recycled fuse, we also have another facility called WATS, Waste to Stable Salts, which is a facility that'll take the existing spent nuclear fuel waste and convert it into the fuel for our reactor. And the big byproducts out of that process are now shorter lived, safer byproducts that are easier to dispose of, in addition to the products that we can use as fuel. And then the third one finally is called grid reserve. This is a thermal energy storage. So it's large tanks of more molten salt. And so the heat that's produced from the reactor can heat up these large tanks of molten salt, which is essentially now an energy storage. It's large tanks of this liquid salt. And so, for example, if you're heating those tanks for 2/3 of the day, so using the energy from the reactor for 2/3 of the day to fill the tanks, then you could have a steam turbine producing electricity at 3 times the capacity for 1/3 of the day. So you're taking that stored heat for 2/3 of the day, and the reactor that's producing heat for 1/3 of the day. So you can produce electricity at 3 times the capacity for 1/3 of the day. So instead of a conventional nuclear power would operate at a 95% capacity factor, just base load, this is a larger power plant that runs at, for example, 30% capacity factor. So it's now acting as a peaking plant to complement or enable more renewables on the grid than would otherwise be possible. And storing heat is much, much cheaper than storing electricity.
Yes, that's what I'm learning. Tell us about the process behind recycling nuclear waste. What's involved in that?
Yeah, so in Canada, we start with CANDU fuel. That's the fuel that's, for example, at Point Lepreau and at the existing reactor sites. We put it through some different chemical processes, and what comes out, or what's called, one of the streams is the transuranic. So it's everything, uranium and everything above uranium on the periodic table, all the artificial elements. And that goes in, that's the mainstream that goes in. We put it into as a salt form, so it comes out as a chloride.
Mm-hmm.
We put it into our reactor as fuel. We cast it into little small pellets about the size of your pinky finger, and they go into fuel pins into the reactor.
Mm-hmm.
The other byproducts then are the original uranium that we started with. That's the main output. That can then be put to side to be used or recycled in the future for other purposes, potentially other reactors, or it can be disposed of in intermediate or even low-level waste, which are much safer and lower cost to dispose of.
Interesting. Because we both know that energy demand is inconsistent. We sleep at night. It's not as busy as it is, like, say, during the day. There's peaks and valleys. How do you manage this while keeping the reactor operating efficiently at a steady state?
Yeah, so some reactors, like the reactors that are in France,
Mm-hmm.
they essentially power down when they want to operate flexibly. And some of the other reactors are looking at doing that, but our design is to run 24/7, so it runs consistently, like the
Mm-hmm.
CANDU fleets in Canada.
Right.
But then with this energy storage grid reserve, you can get that flexibility on the grid, so you can follow the load really. And what we sell or we design is a standard reactor and waste recycling facility, and the customer can have whatever size storage or flexibility they want. So if one customer just wants the baseload electricity, we wouldn't need the storage because that has additional cost, even though it's cost effective. It is additional cost. As one customer wants baseload, and maybe the industrial heat users would want baseload, but other grids that have a lot of renewables on them, for example, the extra storage and capacity would be very valuable because you can follow the peaks, which is follow the price.
Right. Interesting. You mentioned earlier about molten salt. I have no idea what that is. Where does it come from? Is it really hot salt? Like we know hot honey, but molten honey, molten salt, like, tell me, what is that?
Yeah. Well, so maybe just come back to conventional reactors. So conventional fuel is little small pellets of uranium dioxide. That's a
Mm-hmm.
ceramic, and they're again about the size of your pinky nail. And there's hundreds of those, thousands of those in the reactors, and each fuel pin there's maybe 100 of them vertically, and they, when they're put together, they get hot, and then water takes that heat away, and then you can create steam to make electricity. In
Okay.
our reactor, we have those same fuel pins, but instead of the little pellets of uranium, we start off with solid pellets of salt, fuel salt. When that's brought up to temperature, roughly above about 400 degrees Celsius, that salt turns to a liquid. And it's totally normal liquid, a totally normal liquid. That's very good for taking heat away.
Mm-hmm.
And so, a molten salt, if you table salt sodium chloride, what is good on French fries,
Yeah.
when you heat that up to around 400 degrees or a bit higher, actually, for sodium chloride, it turns into a liquid like water. It is transparent and flows like water.
Really?
So that would be, we use part sodium chloride, but other salt compounds like magnesium chloride and potassium chloride.
Mm-hmm.
But yeah, it's a liquid like that. We also use another molten salt to take the heat away. So we could use water or gas or any coolant. We've chosen another molten salt to take the heat away. And then you can make steam with that to produce electricity, but we could use any medium.
That's really interesting. Tell us what happens to the waste once you've used it, used to produce energy. Like, it's all spent up. Like, what do you do with it then?
Yeah, so I mentioned that we take the original spent CANDU fuel and
Mm-hmm.
put that through our process, and then we have the small part of that, which is the long-lived parts of the original waste, now goes into our reactor and is used as fuel. When that's used as fuel, it's literally destroyed. It's Einstein's equation, E equals mc squared. You're turning matter into energy.
Right.
There are byproducts, which is called fission products. There are other elements that do get produced that have that are radioactive for 100 or a couple of 100 years that we need to dispose of. So every nuclear fission process has some level of those byproducts. But the really long-lived plutonium and the unnatural elements above uranium, they're the ones that in our reactor, we can destroy them as we convert them into energy and
Right.
ultimately get rid of them. So the spent fuel then comes out of our reactor, and we can put that back around into our recycling process again and keep doing it. That's a loop. So it comes out
Right.
of our reactor, gets topped up with spent CANDU fuel, it keeps going round and round again. And it's continually destroyed. Each time it goes through, we're destroying a bit more and a bit more. And then when our reactor is done after its 60-year life, there's a spent fuel that comes out that's in the core then that can either go back into another reactor and you keep the process going again, or you could dispose of that in a deep geological repository if that was what the customer or government wanted to do.
What's next for Moltex Energy? I know you guys are working on some really cool things up and coming. So what's next?
Yeah, so it's been a fun few years. We're building up the team here and really validating the main design and the novel parts of the design. We've completed the first phase of the Canadian regulatory process called the Vendor Design Review. Mm-hmm. And now we are in expand mode. We're building the team and progressing the design to get ready for the second phase of the regulatory process to validate the design. And there's lots of different tests we need to do. So we've done all the main fundamental tests, but now it's just scaling those up because nuclear is very heavily regulated, as it should be, and we have to have everything tested out and really validated before we can get contemplate actually building the first demonstration reactor. And so that's the testing we're doing over the next few years and the design work. And then MB Power, our main customer, will be submitting license applications using all that data and design that we've been producing to be able to get a license to demonstrate the first reactor at Point Lepreau.
Well, that's exciting. I'll be cheering you guys on. That's really, really wonderful news.
Thank you. And then after that, so the New Brunswick is the first one. There's a long list of customers that are very interested in this product because a lot of operators and governments around the world have a lot of nuclear waste.
Right.
And so the spent fuel in Canada is enough to power about 6 gigawatts of our reactors, 6,000 megawatts. I should know how many homes that is, but it's a lot of energy from the spent fuel.
Right.
And globally, that's about 120 gigawatts of energy just from the waste that's sitting around at existing sites. And if there's more nuclear power, that means more market share for us and more reactors that we can build.
Absolutely. That sounds really interesting. I never would think that nuclear waste could be, kind of put into a loop and recycled in this way. Thanks a lot.
There's a lot of energy there that we want to use.
Yeah, there is. Well, thank you so much for your time today, Rory, and I wish you all the best success. And thanks for being a guest today.
Thanks for having me, Maria.
That was Rory O'Sullivan of Moltex Energy Canada joining us today. Thanks again, Rory. And also, what are your thoughts on today's episode? Send us an email at podcast@sociablemedia.co. Thanks again for your time and listening today. We'll talk to you next time.